Alright, this video is on actually how to do light problems and light equations and go through that. The items you guys will need to do these problems are paper and a calculator. And we're basically going to use the two light equations. If you're having calculator issues, make sure to watch the calculator video that I posted that walks through all the steps for how to use your TI-30X. Alright, so to briefly summarize, there are two light equations. C equals lambda times nu. And again, my apologies. Unfortunately, explaining everything doesn't have the lambda or the nu key, so it comes up funky. And then the other equation is E equals Planck's constant times nu, where speed of light will always be given to you guys, 3.00 times 10 to the 8th. And Planck's constant will also be given to you, 6.63 times 10 to the negative 34. And then 1 nanometer is going to equal 1 times 10 to the negative 9th meters. I'm going to go through this problem pretty quick because this was actually on the calculator item. So we have C equals lambda times nu, E equals h times nu, speed of light, and Planck's constant, and this. And then what we're trying to determine is the light given off by a wavelength when we have 600 nanometers. Now the first step with any wavelength is you must convert that wavelength to meters. Whatever that wavelength's in, you must convert it to meters. To do that, in this one it's nanometers, so you're going to have 600 nanometers on top. The conversion is 1 times 10 to the negative 9 meters equals 1 nanometer on bottom. Nanometers cancel out, so we'll multiply that together. And then our wavelength in meters is going to be this. And again, I walked through on the calculator on how to accomplish that. And again, because this is in meters and speed of light is in meters per second, we can now get a frequency. So when we set this up, I'm going to put a check by speed of light because we have that, a check next to wavelength because we have that, and then we can solve for frequency. So what's going to happen is that we will divide everything. So 3.00 times 10 to the 8 meters per second divided by 6.00 times 10 to the negative 7 meters, and that's going to get us, again that's just a mistake, 5.00 times 10 to the 14th per second. And again, per second is also equal to hertz, as we talked about in class, which is the number of waves you're going to get per second. Then what's going to happen is, what's going to be the energy associated with this? Well, again, we have h times nu. Planck's constant's given. So what we'll do is we will multiply 6.63 times 10 to the negative 34 times 5.00 times 10 to the 14th. And in appropriate significant digits, we're going to get 3.32 times 10 to the negative 19 joules. So that'll be our answer for B, which is the energy. Problem 2 is almost exactly the same problem, only instead of 600 nanometers, we're going to have 800 nanometers. So we're first going to get the frequency. The second thing we're going to get is the energy. So what's going to happen is again, we're going to convert the wavelength to get into meters. And when we actually do that, when you set that up, it's going to be 8.00 times 10 to the 7th. So again, that 800 nanometers. And it's 1 times 10 to the negative 9th. Will be over 1 nanometer. So you take 800 times 1 times 10 to the negative 9th, you're going to get 8.00 times 10 to the negative 7th. So what's going to happen is you're going to take speed of light, which is 3.00 times 10 to the 8th. You're going to divide by 8.00 times 10 to the negative 7, and that's going to get you a frequency at 3.75 times 10 to the 14th per second, or hertz. To do the energy, because energy is Planck's constant times nu. So Planck's constant is 6.63 times 10 to the negative 34. And then what's going to happen is our frequency is 3.75 times 10 to the 14th. So we're going to multiply those two together. And when you do that in appropriate significant digits, you're going to get an energy value of 2.49 joules, because seconds are going to cancel out. Our third problem, now we have a microwave. which is in millimeters, but same setup. Okay, the equations will be the same. The givens will be the same. What we need to do is now we need energy. So we'll first have to solve for frequency. So I'm going to first solve for frequency. And then the second item, we're going to use the frequency equation to solve for energy. What happens is I'm going to convert into meters. 122 millimeters is going to be 0.122 meters. So that's going to be the microwave. Then what we're going to do is take speed of light divided by that. So 3.00 times 10 to the 8th meters per second. We're going to divide by that 0.122. Meters is going to drop out, and we're going to get 2.46 times 10 to the 9th per second, or hertz. What we're going to do is plug this in to the equation. So E equals Planck's constant times nu. Again, we have the frequency is at 2.46 times 10 to the 9th. Then we just need to plug everything in. So 6.63 times 10 to the negative 34 joules times seconds times 2.46 times 10 to the 9th. And what you should get is this answer right here. So again, if you're having calculator issues, look at that calculator thing. Through these three problems, this is pretty much what you're going to see as far as light equations go. That again, everything's about multiplication and division. You're working with the two equations. You're working with those variables. If you have any questions, you can ask them in class or stop by to see me. Alright, that wraps up the light problem video.